The rest of this chapter is really just ways to calculate our enthalpy change. Remember, our enthalpy change was the heat of our reaction. So delta H, right? If it was a negative value, our system lost heat energy, it's exothermic. If our enthalpy change is positive, our system gained heat energy, it's an endothermic reaction. And one of the ways that we can calculate the heat changes that occur with our reaction is using a process called calorimetry. Most general chemistry labs do have a calorimetry experiment that you would do. And in lecture, we're just going to go through the calculations on how to do that. So it's an experimental technique. Used to determine the energy changes associated with a process. It takes place in a device called a calorimeter. And a calorimeter is basically just an insulated container that has a way to measure temperature. So generally a thermometer. So an insulated container. If you're in a nice research lab, it's generally really fancy and expensive with a digital thermometer in it. In a general chemistry lab, often we'll just use a styrofoam coffee cup. So some sort of insulated container that we can measure temperature changes. So we measure temperature changes, and then using that temperature change and then the specific heat or heat capacity of our substance, which are new terms that we'll define shortly, we can calculate the heat that enters or leaves the system. So we're going to measure or observe a temperature change that occurs and use to calculate heat changes. Remember that temperature and heat are different, right? Temperature is the average kinetic energy. Heat is kind of our total, right? Remember the coffee cup and bathtub, right, of boiling water are both 100 degrees. They have the same temperature, but there's more heat associated with a bathtub of boiling water, right, than there is with that coffee cup. So we're going to use the temperature, though, to calculate the heat. Couple new terms I said I would define. One is a heat capacity. And the typical abbreviation for heat capacity is a lowercase c. And heat capacity is defined as the amount of heat required to raise the temperature of an object by a given amount. It's the amount of heat needed to raise the temperature of an object by a given amount. And that's going to depend on what that object is, right? If I wanted to raise the temperature of water by 1 degree Celsius, it's going to take a different amount of heat than if I wanted to raise the temperature of a block of aluminum by 1 degree Celsius. So again, it depends on what that substance is. So heat capacity, amount of heat needed to raise the temperature of an object by a given amount. And to calculate our heat capacity, it's going to be equal to Q. Remember, Q is my heat transfer divided by delta T, which is my temperature change. Again, remember, every time we see delta, it's going to represent change in this chapter, and it's always going to be final minus initial. So my final temperature minus my initial temperature. Typical units are going to be joules, which is our SI unit, right, for heat, for energy, right? Heat is a form of energy. And then either divided by degrees Celsius or by Kelvin. Be really careful here. They're the same thing, right? It's the change in temperature, not the temperature, right? And remember that 1 degree Celsius is actually equal to 1 degree Kelvin, right? If we went up by 1 degree Celsius, we also went up by 1 degree Kelvin. Remember that 1 degree Fahrenheit and 1 degree Celsius are not the same, right? The one is, 1.8 times bigger than the other, but 1 degree Celsius is equal to 1 degree Kelvin. So maybe we'll do an example. I've seen a lot of students get this wrong. So if we wanted to know what is the temperature change in Kelvin when the temperature goes from 20.0 degrees Celsius to 20.8 degrees Celsius. So I'm honestly, the way I'm going to do this, and I'll explain, is I'm just going to take my final, I'm going to subtract my initial, I'm going to get 0.8 as my answer, and I'm going to change it to a Kelvin. I'm not adding 273 to 0.8 to get it to Kelvin because it didn't change by 273.8 degrees Kelvin, right? If I wanted to convert my temperatures to Kelvin, I would have to add 273 to my temperatures. So I would add 273 to this number. I would add 273 to this number. So let's actually do that. So if I take 273, I'm just typing into my calculator right now, and I add 20.8 to it. I guess we probably didn't need the calculator for that. I get 293.8 Kelvin. I would then add 273 to 20 degrees Celsius, and I would get 293.0 Kelvin. And then when I subtract that, I get 0.8 Kelvin, right? It doesn't matter because I would add 273 to this number, and then I would add 273 to this number, and then when I subtract them, the 273s kind of negate each other, right? It doesn't matter. What I see people do, and this is where you're going to go wrong, is they add 273 to this, and they say the change is 273.8 Kelvin. That's incorrect, right? My change, delta T, is 0.8. So I actually don't need to change the temperatures if I'm from Celsius to Kelvin, if I'm solving for a temperature change, right? If that makes sense. My answer, whether I added, right, as whether I left them as degree C or whether I changed them to Kelvin, comes out to be the same thing. So from a unit perspective, those are actually the same because it's temperature change on the bottom, right? Delta T. It's not T, it's delta T. And my change, whether it's in Celsius or if it's in Kelvin, is going to be the same thing. I also wanted to find specific heat. And specific heat is very similar to heat capacity, but it's specific to the amount, actually the mass of my substance. So this is going to be the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin, right? 1 degree Celsius, if it goes up by 1 Celsius, right, it's also gone up by 1 degree Kelvin or down. So specific heat, the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin, again, those being the same amount. So this time when I write my equation for it, right, my specific heat, and we're going to use, this is how the back of your periodic table is abbreviating it, so it's using SH for specific heat. It's going to be equal to Q, but then this time I'm going to divide it by my temperature change and my mass, right? Grams are part of that. My units are going to be joules per gram. It doesn't matter if it's delta T first or mass. You could swap these. So you could do degree C times grams, right? Or joules per gram Kelvin. Again, those being the same thing. I could also take both of these and rearrange them to solve for Q, right? Q would be equal to, I'm just going to multiply both sides by delta H and my mass. So my specific heat multiplied by my mass multiplied by delta T. If we went back up to our heat capacity one, right, if I wanted to solve this for Q, I'm just going to take, right, C and multiply it by delta T. The way that these equations are found on the back of your periodic table, and they are on your periodic table, they just look a little different, is they're combining them, right? Q is equal to this, and then Q is also equal to this. So on your periodic table, they're actually putting it in one line. And they're using M for mass, which is kind of weird, but that's how your periodic table's doing it. So if you look on your table on the back, it has Q is equal to M, which is what they're using for mass, it multiplied by specific heat, multiplied by your temperature change. And then that's also equal to my heat capacity multiplied by my temperature change. So it's just taking both of these. I just want to, if you're using your periodic table to find these equations, it's taking both of these and then just writing them in one line. So this is my mass. This is my specific heat. So Q is equal to those things, right? Times my temperature change. Or we could say Q is equal to this, my heat capacity times my temperature change. That's this one, right here. So it's just, again, combining them in one line. And then it's using M for mass instead of mass. So do be careful for that. I do want to go through a couple examples. So our first one, we're going to calculate the heat needed to raise the temperature of 32.8 grams of iron by 12 degrees Celsius. The specific heat of iron is 25.1 joules per gram degrees Celsius. So we're solving for heat, that's going to be Q. So I'm just going to grab this equation from the back of our periodic table. We know that Q is going to be equal to M, which is representing mass, multiplied by my specific heat, multiplied by my temperature change. And we're given all the information for this one, right? I'm not given the temperatures, I actually am given the temperature change. So my temperature change is going to be 12 degrees. So delta T, 12 degrees Celsius, right? My mass is given to us as 32.8 grams. And then my specific heat, which is S sub H, is 25.1 joules per gram degrees Celsius. We would just want to double check our units. If for some reason the mass was given to us in kilograms, we would need to convert it to grams, right, to get my units to cancel. We want to make sure that my temperature changes are all correct. So again, just really double check units. That's about the only way to make this part harder or more difficult. I'm plugging all that into my equation then. Q is going to be equal to my mass, which is 32.8 grams, multiplied by my specific heat, multiplied by my temperature change. My grams are going to cancel. My degrees Celsius are going to cancel. I'm going to be left with joules, which is my unit of energy. So 32.8, I'm just grabbing my calculator and typing it in, multiplied by 12, gives me a big number, 9,879. I'm just writing the entire thing down, 0.36 joules. I do want to round this to two significant digits. I do just have 2 here in my temperature, so that's my smallest number. And then it doesn't specifically say to convert it to kilojoules, but I'm going to. So I'm going to convert this. I want to end it here, and I'm also going to convert it to kilojoules at the same time. So I would divide it by 1,000. So to convert to kilojoules, right, we can just move our decimal place over. So I'm going to have 9.9 when I round it to the correct number of significant figures, kilojoules. If you wanted to leave it in joules, 9,900, right, joules. And that would be fine also, since the question didn't specify. I do want to do a more involved example next. What we're doing in this example, while we're calculating the amount of heat needed to raise it, we're ignoring the fact that perhaps this is taking place in a container, right? Some sort of device. And that device could also be absorbing heat energy. So the total amount of heat that we need sometimes is going to be slightly different depending on whether my device is absorbing heat or not. So kind of the way I want to think about it is that if I have an exothermic reaction, remember, if it's exothermic, that means my system is losing heat energy, right? Heat energy is released. My enthalpy change is a negative value. And remember, total energy is conserved, so any heat released by my system is going to be gained by my surroundings. And in this case, my surroundings is both my calorimeter. It can absorb heat. Expensive, nice ones absorb minimal heat. Coffee cups are going to absorb some heat. And then my solution is also going to gain heat energy. Remember, my surroundings is both the solution that my substance is in and the container that it's in. So if I have an exothermic reaction, heat that's released by my system is going to be gained by my surroundings. In this case, my surroundings is going to consist of both my calorimeter and my solution. So heat absorbed by the calorimeter plus the heat absorbed by the solution. Often the heat absorbed by the calorimeter is negligible and we could ignore it, but I want to do an example where it's not negligible, where we can't ignore it. So this is going to be kind of long to write down, so just bear with me as I write down the entire example here. So I'm going to have 50.0 milliliters of a 0.400 molar copper sulfate solution, and it's mixed with 50 milliliters of a 0.600 molar sodium hydroxide solution. And that's mixed at 23.35 degrees Celsius in a calorimeter. Forgot a part. In a calorimeter with a heat capacity of 25.0 joules per degree Celsius. There is more, but I'll give you a second to get caught up. So 50 milliliters of a 0.400 molar copper sulfate solution, copper 2 sulfate solution, is mixed with 50.0 milliliters of a 0.600 molar sodium hydroxide solution at 23.35 degrees Celsius in a calorimeter with a heat capacity of 25.0 joules per degree Celsius. The final temperature of the solution is 26.65 degrees Celsius, and we're going to calculate the amount of heat evolved, just means given off, in this reaction. We do need a little bit more. The solution density is 1.02 grams per milliliter, and the specific heat of the solution is 4.184 joules per gram degrees Celsius. Which, if you remember our definition for a calorie, right, it was the amount of heat that we needed to raise 1 gram of water by 1 degree Celsius. This is a pretty dilute solution, right? My concentration isn't very high, so my specific heat of my solution is very similar to the amount of energy that it takes, right, to raise 1 gram of water by that same temperature. So hopefully you guys have gotten all that written down. If you haven't, please pause and catch up. So we know it's an exothermic reaction because my temperature, right? Remember, the thermometer is stuck in the solution. I'm measuring the temperature of my solution, which is my surroundings. And it's going from 23.35 to 26.65 degrees. So the temperature of my solution, which is my surroundings, is increasing, meaning my system is losing heat, so it's exothermic. I do have a calorimeter that we're listing a heat capacity for. If you're given a heat capacity for your calorimeter, it is absorbing some heat. So what we're going to have to do is this up here. I'm going to calculate the heat absorbed by the calorimeter. Since I'm given a heat capacity, I'm going to use that calculation that had heat capacity in it. So I'm going to take C, which is my heat capacity, and multiply it by my temperature change, and that's going to give me the heat absorbed by my calorimeter. The heat absorbed by my solution, since I'm given a specific heat for the solution, I'm going to use that equation. This is kind of the clue as to how we're going to solve it. So my mass times my specific heat multiplied by my temperature change. Once I get both of those, I can add them together and then change the sign, right? Heat absorbed is going to have a positive value. I'm solving for heat released, so it's going to have a negative value. Total energy is conserved, right? So total energy absorbed is going to be equal to the total energy released. So that's kind of my plan. So let's do heat absorbed by the calorimeter first. So heat absorbed by the calorimeter. We're going to use this equation. And again, my clue to use that equation, if I read the problem, is that I'm given a heat capacity for the calorimeter. Since I'm given a heat capacity, I'm going to use the equation that has heat capacity in it. I do need my temperature change. It's going to be the same temperature change for both of them, so we'll just do that here. So my temperature change is going to be my final temperature, so 26.65 degrees Celsius, minus my initial temperature, which was 23.35 degrees Celsius. So 3.3 degrees Celsius is going to be my temperature change. So heat absorbed by the calorimeter is going to be my heat capacity, which is up here somewhere, 25.0 joules degrees Celsius, multiplied by my temperature change. My degrees Celsius are going to cancel. I'm grabbing my calculator. And I get 82.5 joules. So that's the amount of energy that is being absorbed by my calorimeter. I'm now going to calculate the heat absorbed by the solution. And again, we're given a specific heat for the solution. So I'm going to use that equation. The specific heat's given to us, we have that part. My temperature change we've already calculated. We do have to calculate the mass. And the way that we're going to do that is I am going to use the fact that I have density given to me, right? Density is grams per milliliter. So if I multiply that density by my total volume in milliliters, milliliters will cancel and I'll be left with the grams of my solution, right? Remember, if we have units, right, that are something over something, in this case, grams over milliliters, we use it to convert between those two things. So since my units are grams per milliliter, we use it to convert between grams and milliliters. Right, molar mass for grams per mole, we use it to calculate or to convert between grams and moles. Right, molarity, moles per liter, we use it to calculate or to convert between moles and liters. So I'm going to use my density. And then I do have to remember that I'm mixing these. So if I go back up, I have to use my total volume. I'm taking 50 milliliters of one, I'm mixing it with 50 milliliters of the other. So my total volume at this point is 100 milliliters. So to get my mass, I'm going to take my total volume, it was 50.0, so 100.0 milliliters. I'm going to multiply that by my density, which is 1.02 grams per milliliter. Milliliters cancel, and I'm going to be left with 102 grams of solution. So that's going to be the mass that I plug into that problem. Or into that equation, sorry. So my heat is going to be 102 grams multiplied by my specific heat, which is up here, 4.184 joules per gram degrees Celsius, multiplied by my temperature change, which is over here, 3.30 degrees Celsius. My grams cancel, my degrees Celsius cancel, and I'm grabbing my calculator. 2 multiplied by 4.184 multiplied by 3.3, and I got 1407. Again, I'm just writing down a whole bunch of numbers. I do only want 3 significant digits in this, so if I leave it at 1407, that's actually 4. So I do need to round, that 7 is going to round that 0 up to a 1. So I'm going to get 4010 joules. You could put it in scientific notation if you wanted. So 1.41 times 10 to the third joules. I'm just going to leave it here because we are going to add it, and then I'll probably convert to kilojoules when I'm done. So again, this is the amount of heat that's being absorbed by the calorimeter. This is the amount of heat that's being absorbed by my solution. If I add those together, that's going to be the total amount of heat absorbed by my surroundings. So adding those together, 1410 plus 82.5, I get 1,492.5. Again, when we're adding, it's the number of digits after the decimal point. So 1493 joules. So this is my heat absorbed, right, by the surroundings. So I'm simply going to put a negative sign in front of it, and that's going to be the heat that I'm releasing, right, by my system. So I have a negative 1493 joules. I am going to convert that to kilojoules by moving my decimal place over. So negative 1.493 kilojoules of heat released. And I guess technically it's kind of redundant to put the negative sign and the word released, right? If it's negative, it is released by the system, right? Total energy is conserved. So if I'm absorbing this much, then I'm releasing that same amount. So this would be my answer for Q, right? This is my total amount of heat released by the system. I am going to add a second part to this question, and that's to solve for our enthalpy change. So we are going to calculate my enthalpy change, which is delta H. And for this reaction, remember that our relationship between Q and our enthalpy change is that I take Q, which is what this number is, right? That's my total heat, and I'm going to divide it by the number of moles. So remember, my enthalpy change is the heat of the reaction. So we do need the specific number of moles for that reaction. So what I need to do is I need to actually write my balanced chemical equation, because I'm given, this one's going to be kind of involved again, because I'm given information for both of my reactants, it's actually a limiting reactant problem. I'm going to have to determine which one's limiting and then use that number of moles to calculate my enthalpy change. So first step is I'm going to write that balanced chemical equation. So going way back up again, I have copper sulfate, copper 2 sulfate, and sodium hydroxide. And this is just a double replacement reaction, just like we were doing in chapter 7, right? Copper has a +2 charge. I know that because sulfate is one of the polyatomic ions that we memorized, and it has a -2 charge. And there's 1 copper for every 1 sulfate. Sodium has a +1 charge, and hydroxide a -1 charge. So we know that we're going to swap partners, right? I'm going to take the copper 2+, and I'm going to combine it with my hydroxide. Because copper has a +2 charge and hydroxide only has a -1 charge, I do need 2 hydroxides for every 1 copper. And then my positive sodium is going to go with my negative sulfate. Because sodium has a +1 and sulfate has a -2, I do need 2 sodium for every 1 sulfate. And then if we were writing ionic and net-ionic equations, right, if we were looking at this as a precipitation reaction just for practice, this would be solid and this would be aqueous using our solubility rules. I am going to balance this. On my product side, I have 2 hydroxide. On my reactant side, I have 1. So if I put a 2 in front of sodium hydroxide, that also gives me 2 sodium, but over here I have 2 sodium, so that helps. I have 1 sulfate on both sides, and I have 1 copper on both sides, so this is balanced. I'm now going to figure out the number of moles of copper 2 sulfate and sodium hydroxide that I have using my molarity and my volume given in the problem. And then I'm going to compare that to the 1:2 ratio that I need to see which one's limiting. Once I get that, we'll then divide it into the number, into my heat transfer to get my enthalpy change. So back up to this because I need this information. So I'm just going to copy it and paste it down. I'm taking the easy way. So copy. And I'm going to paste it so we don't have to keep scrolling back up. So I do have 50 milliliters of a 0.4 molar solution. Remember that molarity is moles per liter. So if I change that volume to liters and multiply it by my molarity, that'll give me moles, right? So moles of copper 2 sulfate right? I'm going to take 0.0500 liters, right? I'm just moving my decimal place over 3 places. If I multiply that by my molarity, 0.400 moles per liter, liters will cancel, and I'll be left with the number of moles. So when I do that, I end up with 0.200 moles of copper 2 sulfate. We'll do the same thing with sodium hydroxide. Moles of sodium hydroxide. So again, convert my volume in milliliters to liters. So 0.0500 liters. Multiply it by its molarity. So 0.600 moles per liter. Liters will cancel, and we'll be left with I lost a 0 up there. Hang on, we'll go fix it. 0.0300 moles of sodium hydroxide. Sorry about that, guys. I lost the 0 here. it's 0.0200 moles. So this is now where I'm going to compare my need ratio, right? According to my balanced equation, I need 2 sodium hydroxide, right? 2 moles of sodium hydroxide for every 1 mole of copper 2 sulfate. What I have is 0.0300 moles of sodium hydroxide for every 0.0200 moles of copper 2 sulfate. And when I divide that out, I get 1.5 sodium hydroxide, drop some sig figs, over 1 copper 2 sulfate. So I need, right? I need 2 for every 1. I have 1.5. So I need 2, I have less than that. So what that tells me is that sodium hydroxide is limiting. Again, what we're trying to do is we're trying to figure out what this number is, right, that I'm going to divide into Q, which is this number, to solve for my enthalpy change. To do that, I need to figure out which one is my limiting reactant, right? We want it specific to the reaction. We don't want the excess. We're actually not quite done yet. Even though this is my moles, keep in mind I do have a coefficient here. So it doesn't say, right, if I look at this equation, it's not Q divided by 2 moles, right? It's Q divided by moles. So what I need to do is I need to scale it down. So I'm going to take my 0.0300 moles of sodium hydroxide, and then I'm just going to divide that by 2 because I have this 2 here in my equation. So I need to scale it down. I don't want 2 moles of sodium hydroxide on the bottom. I want it per mole, right? Not per 2 moles. So I am going to divide that by 2, and I'm going to get 0.0150 moles. And then that's the number that we're going to divide into Q to get my enthalpy change. So almost done, I promise. Delta H is a negative, going back up, I'm taking this number. So negative 1.493 kilojoules. I have 0.0150 moles. And then I'm going to grab my calculator. We'll divide that out. And I got a negative 99.5 kilojoules per mole. So that would be my enthalpy change, right? The heat of reaction for this problem. It's a negative value because it's an exothermic reaction, right? My system is losing heat energy. That heat energy is being absorbed by the calorimeter and my solution. I do want to go through another example, something a little bit different, but still involving calorimetry. So in this one, I have a metal with a mass of 125.0 grams, and it's originally at 105.3 degrees Celsius, and is dropped into 100.0 grams of water at 23.9 degrees Celsius. So what I have is I have 100 grams of water in a container, and the temperature of that water is 23.9 degrees Celsius. I have a piece of metal, right? The metal has a mass of 125.0 grams, and its temperature, right, it's hot, it's 105.3 degrees Celsius. And I'm taking that hot metal and I'm dumping it into the water. That's going to change the temperature, right? The final temperature is 40.6 degrees Celsius, and they're going to reach the same temperature. So that's going to be the final temperature of both of them. So it's going to kind of sit a little bit, it's going to equalize, and my final temperature is going to be 40.6 degrees Celsius. We're given the specific heat of our water. So the specific heat of water is 4.184 joules per gram degree Celsius. And we're going to calculate the specific heat of the metal. So looking at our specific heat equation, right, I have Q is equal to my mass multiplied by my specific heat multiplied by my temperature change. So if we're solving for the specific heat of my metal, right, this is my unknown, I have the mass that's given to me in the problem, right, 125.0 grams. I can calculate the temperature change. My problem is I don't know Q neither, right? I don't know my heat transfer. So I have two unknowns, which is problematic. Luckily, though, we do have the law of energy conservation, right? We have the first law of thermodynamics, and that tells me that the total amount of heat, right, that's being lost by my metal, and I know my metal's losing heat because it's going from 105.3 degrees to 4.6, is going to be equal to the total amount of heat gained by my water. We know water is going from 23 to 40.6. So using the first law of thermodynamics, Q for my metal is equal to Q for my water, right? The heat absorbed by one is being lost by the other because total heat is conserved. So what I can do is I can write essentially this equation twice, once for the water, once for the metal, and set them equal to each other. And then I don't have to worry about Q, right? Q is not part of my equation. So I know that the mass, right, for my metal, this is a subscript, is going to be equal to, multiplied by the specific heat for the metal, again, subscript, multiplied by the temperature change for my metal. That's going to be equal to the mass of my water multiplied by the specific heat of my water multiplied by the temperature change for my water. So I can now just plug all those numbers in. So the mass for my metal going up to my problem is 125.0 grams. The specific heat for my metal is my unknown. The temperature change for my metal, I'm going to have 105.3 degrees Celsius minus 40.6 degrees Celsius. And you could calculate that first and then just plug in the change, which we probably should do because I'm going to run out of room. Let me move this over a little bit and see if we can squish it in. Mass of my water, if I go up, it's here somewhere, 100.0 grams. Multiplied by the specific heat of my water, also given in the problem, 4.184 joules per gram degrees Celsius, multiplied by its temperature change, which is going to be the 40.6 degrees Celsius minus the 23.9 degrees Celsius. Kind of fits. From a sign perspective, I'm going to go kind of back up and look at this. Often, because remember, signs are just telling me the direction and not the magnitude. So I often, when I'm doing the math, kind of tend to ignore the signs and then put them in as I need them. So if we go back up to look at this, the metal's actually losing heat. So there's actually a negative value here. So remember, the Q's are equal, right? If one is gaining 70 joules, the other is losing 70 joules. So if I put a negative sign here, then I'm saying that the heat released by the metal is equal to the heat absorbed by water, which means when I go down to my problem here, I'm kind of losing space here, but I would have a negative sign out in front of all of this. What I'm doing is I'm ignoring that. I know that my specific heat needs to come out to be a positive value. Specific heats are always going to be positive, right? It's the amount of heat that we need to raise the temperature, right, of 1 gram of a substance by 1 degree Celsius. You're not going to use a negative amount of heat to raise a temperature. So specific heat always needs to come out positive. I know that my temperature change is always final minus initial. And if I look at water, right, my initial temperature was this number, my final temperature was this number. So I do have this set up correctly. However, for my metal, this was actually my final and this was actually my initial. So those should actually go the other way, which would give me a negative value for my temperature change. And then if I had the negative sign here, the negative times the negative gives me that positive value. What I'm choosing to do is ignore that negative and then just put this part in the order that gives me a positive value, and then my specific heat comes out positive. If that's confusing as to why I'm switching, this order, then by all means, do it the right way. Just make sure that you have that negative value at the beginning, right? If I don't have that negative there, then if this is in the other order, my sign is going to come out incorrectly. So again, kind of what I'm doing is I'm just noting the fact that my specific heat has to be positive, and then I'm doing my temperature changes in a way that gives me a positive value. If you did your temperature change the other way and your answer came out negative, then just get rid of the negative. Just ignore it, because specific heat has to be positive. Hopefully that made a little bit of sense to you guys. So I'm gonna grab my calculator here, but I'm gonna do the temperature changes first. So I'm gonna take 105.3, I'm gonna subtract 40.6 from it, and that gives me, for this number, a temperature change of 64.7. It's actually going down by 64.7 degrees, but again, I'm ignoring that negative sign. Again, the sign just tells me direction. I'm going to figure out my temperature change on this other side. 40.6 minus 23.9. And that gives me a temperature change of 16.7. Both of them are in degrees Celsius or Kelvin. Okay, now I'm going to do the math, or the rest of the math. So it would be good to pause and do this yourself. Make sure you can get the same answers as me. I'm still typing. This one takes a little bit. And hopefully you guys got that your specific heat for the metal is 0.86. And I do want 3 significant digits, 4. And then my units come out to be joules per gram degrees Celsius. So unit-wise, these grams end up canceling each other when you do the math. This degree Celsius cancels with this degree Celsius, and then you're just left with those as your units. So the specific heat of my metal, 0.864 joules per gram degrees Celsius.